Okay, let's do tangent planes. This is our next topic. And this is very similar to the tangent lines that you were working with in single variable calculus when you get those first derivative from a function. If you remember, you had something like this. It's a graph, and maybe you have this half parabola. And if you remember, you have that f of x equals x squared. And if you remember that f prime of x was equal to 2x, and 2x was the derivative for this function. And if you evaluate this 2x in this curve, for example, in this point where x equals some x sub 0 value, then the result of this with 2x at this point was the tangent line to the curve in that specific point, something like this. So this is the tangent line in this specific point for this curve, and the derivative was or is the function that we came out with from this original x squared curve. In the three-dimensional space, it's almost the same. The only thing that changes is that in this first example, you had only a single independent variable and a single dependent variable. So you have a two-dimensional space. In this case, you have a plane. When you draw this line and you have the tangent line right touching but not touching this curve. In the three-dimensional space, let's see how it works. This little blue surface, this is the curve like this one, but in the three-dimensional space. So let's suppose that we have this surface. This blue one surface is the one that you are seeing here. And let's name that surface S. And for that surface, the equation is z equals f x of y, x and y. If you see here, it's the same. With single variable, you have f of x, which is equal to x squared. And in this case, because we have a two variable function, we have this z dependent variable as a function of x and y. And let's suppose that this function has a continuous partial derivatives. So it is continuous all along the domain that we are working with. In the y-axis and the x-axis, the domain is continuous. So we can be sure or confident to say that the partial derivatives for this function exists for any value of x or any value of y. Now, once we are clear with that, let a point P, let me change the color and the pen color here. Let's see, this is the point P. And this point P is located at some point x sub 0, y sub 0, z sub 0. Let's replace these numbers with any coordinate in this 3D space. So you can locate this point P right in this 3-axis coordinate. And let that point P be a point on the surface S. So this point is right on the top of that surface. Okay. Now let C1 and C2, as you see here, this is C2 and this is C1, be the curves obtained by intersecting vertical planes y equals y sub 0 and x equals x sub 0 with the surface S. What's that mean? That mean if it is the same if you can cut this surface with a flat plane this way and in this way. So you can get a curved line across the surface in the x direction and another one in the y direction. So these curves are aligned with these T1 and T2 lines, but are following the surface from this point till the end. So that's the curves. And there's a curve because it's the same as we are describing here in the first example that we show. So that's the curve 1 and the curve 2. Now, let T1 and T2, which is T1 and T2, be the tangent lines to the curve into C1 and C2 and point P. Okay? If we do that here, we can say that this line here, this one is T1, this curve here is C1, okay? And this point here is point P. The only difference is that here we have a single axis and here we have two axes and they are crossed because one of them is going in the x direction and the other one is going in the y direction. Okay, once we are clear with that, T1 and T2, we have two tangent lines, one tangent line for x and one tangent line for y. If we draw a plane all over this T1, T2 lines, because this T1 is tangent to C1 and this T2 is tangent to C2, then all the plane that we can form or construct with these two lines is tangent to the surface at point P. Okay? Now, the tangent plane is formed by the tangent lines T1 and T2, and that's the tangent plane to the surface at point P. I hope and I expect that this is enough explanation. As you remember, uh, regarding the point P, you already have done these calculations before. Any plane, if you remember, any plane passing through any point P in a three-dimensional space has the equation for the plane. If you remember, the equation for the plane that you were working with in the last month was something like this. You have a constant number times the difference from the point of reference with x plus the y-axis plus the z-axis equals 0. You have done this a lot of times, so this is something that you must be familiar with. This is the equation for the plane, and you know how to calculate that using vectorial operations. So you know that any point passing for every plane has this type of equation. Okay, so if we divide this equation by c, because we need to rearrange this in order to connect this with the partial derivatives and tangent planes, let's do some changes to this equation so we can we can have this equation here. First, let's work it out here. We have a times x minus x sub 0 plus b times y minus y sub 0 plus z times z minus z sub 0 equals 0. Okay. Um, the operation that we are going to perform is that we need to simplify this equation because this part over here is the dependent variable. So we need to isolate this to the right. So if we do that, let me erase his. Let's just erase this part here. And this is going to be equal to um, minus z times z minus z sub 0. Okay, so this is the first step because this is the dependent variable. So we need to do as all this guys here equals to this one. And then let's divide all this, divide by c. If we divide by c, then we will get something. If we change the signs and we move this to the left, we can have this z minus z sub 0 equals, we change the sign here, we divide by c, we can get rid of this c, and we will have something like this, minus minus a over c times x minus x sub 0 plus minus b over c times y minus y sub 0. Okay, now if we get rid of this parenthesis here, we can have this as negative. So this is something like a divided by c times x minus x sub 0 minus b divided by c times y minus y sub 0. Okay, and let's replace these values here because this is constant values, and let's replace that with a and with b. Okay, so if we replace that and we keep this as the dependent variable, we can come up with this new expression. So this is our new expression. We are replacing minus a divided by c with an a and minus b divided by c with a b. So now we have z minus z sub 0, which is the change of the dependent variable that is equal to some constant a times the difference between 2 points in the x-axis plus b times the difference between 2 points in the y-axis. And if you see here, this is very similar to that old uh, point slope form that you have working with back in your junior high school days. You can have that uh, formula from your old books that was the point slope form. Okay, so this is very similar to it, but this is in a three-dimensional space. If you are going to work with more than 3 or 4 or 5 variables, you will have this expression a little bit longer, but at the end of the day is the same. Okay, so this is the same form that you were working with the single variable in the point slope form, and this is kind of a special case for this in the three-dimensional space. So in this case, this a and b are known as the rate of change of these two variables in the three-dimensional space or in the function. So now with this, we can set up our equation, because if you remember in the past, all that old point slope was something like this. You had that y minus y sub 0 equals the first derivative evaluated at x sub 0 times x minus x sub 0, and this was the point slope form for that single variable function. So this is very similar to this. What we are going to do is we're going to add more variables, and we are going to replace this a and b constant by their derivatives. So we are going to come up with this, which is any point c minus z sub 0 is going to be equal to the partial derivative with respect to x evaluated at these points times the difference between the point of reference and the original point plus the partial derivative of the function with respect to y evaluated at the point of reference times the difference between the point of reference and the value of interest. And this is the equation for the tangent plane. Okay, that's the equation for the tangent plane. Okay, um, in the next lecture, we are going to work an example regarding this. Please take note of what we are covering in this lecture. There's a lot of material pending to cover in our class, and we are going to do our best between all of you and me to finish this in a proper way. Stay safe.